Hello everyone. Today I'm going to talk about a research paper that broke the internet. So in 2017, 8 researchers at Google published this paper, and the title is literally just 5 words. Attention is all you need. And I'm not even exaggerating when I say this, that this thing has actually created ChatGPT, Dali, and basically every AI you have ever heard about in the last few years. And look, I get it. It's kind of complex, but let us try to understand it together, shall we? All right, so before this paper even came out, if you wanted to use AI to translate languages, you use something called RNNs, which is recurrent neural networks. And the problem with RNNs is that they process things sequentially. Like imagine you're reading a sentence word by word, and you can only move to the next word after you have fully processed the current one. So if I'm at word 100, I had to have already processed the word 1 through 99, every single one. And this creates massive problems. First, you just cannot parallelize anything. Like modern GPUs that are insanely powerful, they can do thousands of calculations all at once. But RNNs, it's like having a supercomputer and it's being using like a calculator from the 90s. The second issue was long range dependency just wiped out. Think about it. If the information from word 1 has to flow through other 99 words in order to reach the word 100, by the time it gets there, it's basically corrupted. It's like that telephone game we used to play as kids. And the third, the training took forever. The best model before this, I think it just took 3 weeks of training on expensive GPUs. So the researchers asked a very simple question. What if the distance did not even matter? What if we could connect any two words in one step? That's what the transformer does. So the core innovation is this thing called attention. And honestly, the name is perfect because it's literally about paying attention to different parts of the input. And here's the formula. Don't panic, I'll break it down for you. So the QKV stands for query, key, and value. Let me give you an example. Say we have the sentence, the animal didn't cross the road because it was tired. So when it hit the word it, what does it refer to? The animal or the road? Your brain instantly looks back the whole sentence and figures it out, right? That's exactly what attention does. So Q is your query, basically what I'm looking for. K is your keys, what is available to match against, and V is your values, the actual content once we find out what we want. So when you do Q, K to the power T, that's just the dot product, which measures how similar things are. The higher the score means, yeah, that's what you're looking for. Now, here's the clever bit. That's square root of D and K in that. The paper has this footnote that is actually really genius. When you're working with like 512 dimensional vectors, the dot products can get huge, like ranging from -22 to +22. And when you feed numbers that big into a softmax function, you'll get outputs like 0.9999 or for one option and 0.00005 for everything else. The gradient becomes so tiny that learning basically stops. So what was the solution? They just scaled it. They divided it by the square root of the dimension while the variance stayed at 1. Then they saw that the gradients flowed properly and everything worked out. The softmax turns these scores into probabilities and multiplied by the values, and boom, you get attention. But wait, it gets better from here. Instead of doing this once, they did it 8 times in parallel, and they call it multi-head attention. So each head can focus on different things. One might track a grammar, another tracks meaning, another handles long-range stuff, the fourth can do local context, and because each head works in smaller dimension, 512 divided by 8 is 64, and that's what the total computation cost, which is the same as doing it all at once. Now you have 8 perspectives for the price of 1. That's magic. So let's build the actual transformer. It got it into 2 parts, an encoder and a decoder. The encoder takes an input sentence and turns it into this continuous representation, while the decoder takes that continuous representation and generates the output, one word at a time. Both of them are made up of 6 identical layers stacked on top of each other, and each layer has this subcomponents with attention. In the encoder, every layer has this multi-head attention where every word looks at every other word. And there is a feed-forward network as well, and around each part they added a residual connection as well, along with layer normalization. So the residual connection is just something like you add the input to the output. Sounds simple, right? But it lets the gradient flow backwards to the network easily. Everything is in the 512 dimension, which matters for these residual connections to work out. The decoder is similar, but it has got like 3 parts instead of 2. And here's the key difference. It uses masked attention. During the training, you have this complete target sentence with you. But if the decoder uses see those future words, it would just cheat and copy them. So masking set the attention to negative infinity for future positions. And after the softmax, those become 0. Each position can now only see the previous positions. Now there is one more crucial thing, positional encoding. Attention is completely order blind. Without positional info, the cat sat is identical to sat cat the. They solved this problem with these sine and cosine functions. different frequencies for different dimensions. Higher frequencies encode nearby positions while lower frequencies encode distant positions. And the cool part is that it's mathematically elegant. The model can learn relative positions using simple linear operations, and they tested learned positions embedding too, got the same results. But the sine cosine version can handle longer sequences than what it saw during the training. Oh, the feed-forward part, just two linear layers with value in between, goes 512 dimensions to directly 2048 dimensions back and down. Simple but effective. So training this thing, they used the WMT 2014 dataset, which contains about 4.5 million sentence pair for English to German. What about the hardware? 8 NVIDIA P100 GPUs on one machine. And what about the training time? 12 hours. So do you think it is a more or less? Well, the previous best model took like 3 weeks. This is like 42 times speed up. They also use diagram optimizer, which is kind of pretty standard, but the learning rate schedule is quite interesting. For the first 4,000 steps, they increase the learning rate linearly. That's called warm-up. And after that, it decays the following this inverse square root pattern. Now you might want to ask why warm-up when everything is randomly initialized at the starting. At the start, big numbers or the learning rates can cause chaos. And gradually increasing it lets things stabilize. They also use dropout, which is like randomly zeroing out 10% of activations, and label smoothing, where instead of saying that this answer is 100% correct, they distributed a bit of probability to other options, makes the model less overconfident. For inference, they also average like the 5 saved models. Use beam search with a beam size of 4 and add a length of penalty to encourage longer translations. That's the recipe. Okay, the results time. From English to German translation, the previous best ensemble model got like 26.36 BLU. BLU stands for Bilingual Evaluation Understudy. So the transformer is just a single model, which has got like 28.4 BLEU. That's insane. Plus 2 BLU is like that's revolutionary in machine translation. And what about the training cost? Well, it is 7 times cheaper than the previous best. What about the English to French? It has got like 41.8 BLEU, another state-of-art result. They also did this ablation studies where they studied out different variations. One variation head doesn't work well. 8 heads, perfect. 32 heads, well, actually worse. Too many. No dropout, well, you're overfitting it. And here's the cool part. They tested it on a completely different task. English constituency parsing, where you're analyzing sentence structure with barely any task-specific tuning, they got 92.7 F1 score, beating almost everything. And this proved that the architecture is actually general purpose, not just good at translation. So why does this work out so much better? It comes down to 3 things. Number 1, computational complexity. For typical sentences with 50 words and 512 dimensional embeddings, self-attention is about 10 times faster than RNNs. The math checks out. Number 2, parallelization. Self-attention can do everything at once. RNNs have to go step by step. And number 3, this is the big one, the path length. Any 2 words in a transformer can communicate in one step. And in RNN, information has to flow through every single position in between. So you can actually see in this attention patterns, like here, the model connects making with difficult across the entire sentence, or here it figures it out that it refers to the law. Different heads learn different aspects, syntax, semantics, dependencies. You can literally watch the model understanding language structure. Well, that's powerful. The paper concludes by saying that they wanted to extend this to other modalities like images, audio, and video, and that's exactly what happened. Let's have a quick look at the timeline. In 2018, BERT revolutionized NLP. In 2019, GPT showed what happens when you scale this up. In 2020, GPT-3 at its 175th billion parameters, and the vision transformers proved that you can use pure attention for images. In 2022, ChatGPT hit its 100 millionth user in 2 months. And in 2023, GPT-4, DALL-E, and all other tools that you have heard about came into existence. So every major AI breakthrough since 2012 is built on this paper. Language models, image generation, video generation, protein folding, code generation, all are transformers. One architecture, infinite application. Now, if you talk about what's the core insight, well, the core insight was actually simplification. They didn't add any complexity, they actually removed it. They deleted recurrence, deleted convolutions, and just kept the attention. Sometimes the biggest breakthrough comes from asking what we can remove it. So yeah, that's a transformer paper. Thanks for watching.